So, good morning all. In this video lecture, we will see what is magnetostatics. So, as I said in the class, a magnetic field is produced whenever an electric charge is in motion. This sentence, a magnetic field is produced whenever an electric charge is in motion. In the presence of steady charge, we cannot produce a magnetic field. We require a charge under motion for producing magnetic field. So, this is a comparison between electrostatics and magnetostatics. Electric field intensity is E, magnetic field intensity is H, electric flux density D, magnetic flux density B. The relation connecting flux density and electric field intensity is D equals epsilon E. Similarly, here also there is a relation connecting B and H. This is also important. B is equal to mu H. We know mu R is equal to mu by mu 0. So, from that mu is equal to mu R mu 0. If the medium is air, then the value of mu R is equal to 1. Mu 0 is 4 pi into 10 raised to minus 7 Henry per meter. Then Coulomb's law, the equivalent in magnetostatics is Biot-Savart's law, Gauss law, and Beer-Circuit's law. Here we were dealing with charge distribution, but here we will be dealing with current distribution. Now coming to Biot-Savart's law, this is the statement. Magnetic field intensity dH produced at a point P by the differential current element IdL is proportional to the product IdL and the sine of the angle alpha between the element and the line joining P to the element and is inversely proportional to square of the distance r between P and the element. And this is a scalar form representation of dH. dH is equal to 1 by 4 pi I dl sine alpha by r square. Scalar form means you will be getting the magnitude of H, not the direction. So, if you want to get the direction of H, then you have to use this formula. dH is equal to 1 by 4 pi I dl sine alpha r by r cube, which is in the vector form. These two forms you have to by heart. This one is more important. Okay. Now, one point that you have to keep in mind is dl will be in the direction of current. Okay, dl and current will be in the same direction. And listen, here across P I have marked a cross mark. That means the magnetic field is acting inwards. Okay. If I have put a dot instead of this cross, then that means the magnetic field is pointing upwards. Okay. So, here I have drawn a current carrying conductor I, and this is my point P. So, when current flows through this current carrying conductor, this point P experiences a magnetic field in the form of concentric circle. And I is the magnitude of the current flowing through this conductor. R is the distance from this conductor to point P. And if I am taking a small length across the circumference of the circle, and if I am drawing a line from that small length to point P, that line will be making an angle with the circle, and that is alpha. These are the terms used in Biot-Savart's law. So, you by heart this statement and write down this expression. Okay. Now, coming to current distribution, this is also very important that you have to keep in mind. In magnetostatics, you have three current distribution, that is line current density, surface current density, and volume current density. Line current density is current per unit length. So unit is ampere per meter. This is current per area. So that is surface density. Here it is current per volume. That is volume current density, and I is used to represent line current density, K for surface current density, and J for volume current density. And here its equivalent electrostatics terminology is written. Okay, this is rho L, rho S, rho V. We already studied it. This C is coulomb, coulomb per meter. It is coulomb per meter square. This is coulomb per meter cube, because the unit of charge is coulomb. Here the unit of current is ampere. And this just shows a pictorial representation of these three densities. If the current is flowing through a wire or a line charge, then it is a line current. And if you take a surface, and if the current is moving through the surface of that body, then it is surface current. And if you are taking a body which has volume, then the current flowing through that body will be volume current density. And these are three formulas for magnetic field intensity in terms of our current distribution, I, K and J, that you can by heart. Now next, coming to Ampere's circular law. This is also important. It is used to find the magnetic field strength. So here I have drawn a current carrying conductor I. Here is a point P. As I said earlier, since the current is moving, it is under motion, this point P experiences magnetic field in the form of concentric circle. And I have chosen a small length dl. Dl you can choose it wherever you want. Okay, so here I have chosen at 4 different points. So here this is 1 dl, this is 1 dl, dl, dl. Okay. So according to Ampere's circuit law, integral B dot dl is equal to mu 0 I, or another way of representing Ampere's law is integral H dot dl equal to I, where B and dl is in same direction. This also you have to keep in mind for doing derivation. B and dl is in same direction, and in the live class I explain how to find the direction of B using right hand thumb rule. And this is the statement of Ampere's circuit law. Line integral of magnetic field around a current carrying conductor is equal to the absolute permeability, that is mu 0, times the total current, that is I. Okay, that is a statement of Ampere's circuit law. Now here you just assume you are placing two conductors, and nearby there is a point P. So obviously when the current flows, what happens is point P will experience magnetic field, and you just assume that the current flowing through these two conductors are in same direction. Then you can modify this expression as integral B dot dl is equal to mu 0 into I1 plus I2, and integral B dot dl is equal to mu 0 into I1 minus I2 if both the currents are in opposite direction. Okay, now we will go back to Stokes' theorem, that is integral A dot dl is equal to line integral of vector A is equal to surface integral of curl of that vector, that is del cross A will give you the curl. Okay, here A is a vector and ds represents a surface area. Okay. So I am replacing this A with another vector H, where H is the magnetic field intensity. H is also a vector. So H dot dl is equal to surface integral of del cross H ds. Okay. Now you know, according to Ampere's circuit law, what is I? I is equal to what? Integral H dot dl. Okay. So if I substitute integral H dot dl instead of I in equation 2, and if I compare equation 1 and 2, then the left hand side will be equal, right? So obviously the right hand side will also be equal. So just comparing the right hand side, accordingly I will get del cross H is equal to J, which gives you Maxwell's fourth equation. Next we will see the applications of Ampere circuit law. Okay. So Ampere circuit law is applicable for symmetric path. So the analogy of Ampere circuit law in electric field was Gauss law. There also I told you the surface should be symmetric and also closed. Right. Here the surface, the path through which the current is flowing should be symmetric. So first we will see the case of hollow cylinder. A hollow cylinder is one in which any given current will be distributed on the surface of the cylinder. That is, there is no current inside the cylinder. This point you have to keep in mind for doing the derivation. Now we will see step by step. First case, I will see the magnetic field inside the cylinder. So here I have drawn a hollow cylinder, and the straight line shows the axis of the cylinder, and as I said, the current is flowing through the surface of the cylinder only. There is no current inside. Now I am choosing a point inside the cylinder which is at a distance small r from the axis. Since there is no moving current, this point P will not experience any magnetic field inside the hollow cylinder, because inside the hollow cylinder there is no current. So since there is no current inside, there is no magnetic field inside. That is case 1. In the second case, I am considering a point P outside the hollow cylinder. In this case, the point P will experience a magnetic field because across the surface of the cylinder, a current I is flowing. So due to this surface current, this point P will experience a magnetic field which is shown in this dotted line. Okay, then I am choosing a small length dl across this dotted line, and also you have to identify the direction of B with respect to dl, and I already told that B and dl are in same direction. So next I am going to find out integral B dot dl, that is equal to integral B dl cos theta. You know, this is a expansion of dot product, since where theta is the angle between B and dl. Since B and dl are in same direction, the theta value is 0, so I can write integral B dl, and since the path is symmetric, B will be constant, so I can take B outside, finally dl. So what is dl? dl is my total length of this dotted portion, that is the circumference of my circle, that is equal to 2 pi r, where r is the distance of the point P from the axis of the cylinder. So I can write B into 2 pi r. Also I know Ampere circuit law is integral B dot dl equal to mu 0 I, that is my equation 2. Now I can compare equation 1 and 2. This side is same. So finally I can write mu 0 I is equal to B into 2 pi r. From that I can calculate B, that is equal to mu 0 I 2 pi r. Next is case 3. In this case 3 I am placing the point P on the surface. And as I said earlier, the current is flowing through the surface of this hollow cylinder. So obviously point P also experience a magnetic field where small r is equal to capital R. So B is equal to mu 0.